This is the third part of AS level physics Edexcel. Um, so in the last two videos, we have reached till the eighth number of the specification. So we'll start with the ninth. Be able to use the formula summation of F is equals to ma and understand how this equation how to use this equation in situations where m is a constant, Newton's second law of motion, including Newton's first law of motion, where a is equal to 0. Okay, so before we begin, there are three laws of the three Newton's laws of motion. First law states that an object that is in rest will remain in rest. An object that is traveling at a constant velocity will remain at a constant velocity unless an external force is applied on the object. What do we mean by this? If you have an object at rest, it will remain at rest. This is because resultant force is 0, okay? However, if there is a resultant force added, okay, F, this object will now face an acceleration in the direction of the resultant force, okay? Say this body is moving at a constant speed of 5 meters per second. When we are at a constant speed, the resultant force is always 0. And if an external force is applied again, force R, there will be a resultant force on the body, hence it will accelerate in the direction of the resultant force. So a body in rest stays at rest, a body in constant velocity stays at constant velocity for both situations, unless if an external force is applied on the object, for which an acceleration will be caused in the direction of the resultant force, okay? That's Newton's first law. Newton's second law. Newton's second law states that the acceleration of an object is proportional to the resultant force experienced by the object. And the acceleration is in the direction of the resultant force, okay? So if you have an object and you have a resultant force of, let's say you have a resultant force of 5 newtons, acceleration will be present. So if resultant force is in this direction, this is resultant force, acceleration will also be in that direction. However, if resultant force is greater, acceleration will also be greater, okay? So that is for the acceleration. That's for Newton's second law. And we can actually use an equation to derive these meanings. F is equals to ma, where F is the resultant force on the object, m is the mass of the object, and a is the acceleration of the object, okay? Next part, Newton's third law of motion. This law states that every reaction has an equal and opposite reaction. That's how you state it in O levels. But in A levels, it's stated as if object A applies a force on object B will apply an equal and opposite force onto object A, okay? If we have two bodies, say, let's just use a ball for this example, and a wall. If this ball hits the wall will push the ball with the same equal and opposite force. However, because the wall has a greater mass, it will face less acceleration by the equation force is equal to ma, which is Newton's second law. If mass is high, acceleration is low, okay? So those are Newton's laws of motions. We're also told to be able to know what terminal velocity is. Terminal velocity is when there is no frictional forces or resultant forces acting on the body. What do we mean by this? Let's take a parachuter, okay? He's jumping off of an aeroplane. This is an aeroplane. And he's jumped off the aeroplane. He's over there, okay? Sorry. And as he falls, his speed will keep on increasing. If we are to draw a velocity time graph, this is shown in the previous video, by the way, velocity against time, okay? He'll start at a zero velocity and he'll increase, sorry, it's not like that. He will increase, but eventually his velocity will become constant. This is because when he jumps, all that is acting on him is his mass, his weight, okay? Hence, he's accelerating due to gravity because he doesn't face any air resistance yet as he's falling, as he begins to fall. As he keeps on falling, however, his weight is the same, but his air resistance increases. He keeps on falling, weight is the same, air resistance increases. It reaches up to a point where his weight and his air resistance that he faces are the same. Hence, a free body diagram will show that he has no resultant force acting on him. For this reason, acceleration will be equal to 0 meters per second squared, and his velocity will be constant velocity. This is referred to as terminal velocity, okay? That's what we mean by terminal velocity. So you can tick this ninth number there. Be able to use the equations for gravitational field strength G is equals to F over M, and weight is equals to mg. This is pretty straightforward. If you'll be given values on force and on mass. At times you'll be given, these equations are both the same thing, okay? Instead of W in this second equation, we have F in the first one. They're both the same equation, just substituted around. This is just about substituting into the equation, and you'll be given these equations in the formula booklet, so we don't need to go through that. Next up, a core practical to determine the acceleration of a free-falling object. This is unit 3 stuff. It can come in your unit 3, so we'll skip this for now. Number 12. Know and understand Newton's third law of motion and know the properties of pairs of forces in an interaction between two bodies. So we've done the first part of it, which is to know what Newton's third law of motion is. Now let's talk about Newton's pairs of forces. Newton's third pair forces. What do we mean by Newton's third pairs of forces? In Newton's third pair of forces, it's basically, first let's start by restating Newton's third law of motion. So for every force experienced by an object, the object exerts an equal and opposite force on the object that is initially applying the force on it, okay? Newton's third pair forces, okay, are two forces that are the same type of forces and have the same magnitude, but they act in opposite directions. Let's give an example. You have a table here, okay? And there is a box on the table. The weight of the box will act downwards, weight. However, there will be a normal reaction force that the table exerts back on the box. These two forces are not Newton's third law forces. Why? Because they're not the same type of forces. R is a normal reaction force, while W is weight. Weight is a gravitational force, so they're not the same type of force, okay? That's important to understand in this case. Some examples of Newton's third pair forces include, one second guys. Yeah. Okay. So some examples of Newton's third pairs of forces include, say you have a man and he is pushing, so you have a man here, okay? And he is pushing a block. He'll apply a pushing force on the block, let's say F1, and the block will apply a push back on him, saying F2. these two forces are the same types of forces and they act in the opposite direction and have the same magnitude. So they are Newton's third law pairs of forces, okay? It's important to notice that if your two forces are not of the same type, then they're not Newton's third law. Like in the first example that we gave here. One is due to gravity and the other one is a normal reaction, so they're not the same type of force. So we can tick that. Understand that momentum is defined as P is equal to mv, okay? So what is momentum? Momentum is the product of mass and velocity. So the equation for momentum is P is equals to mv, where m is the mass and v is the velocity, okay? Your quantity SI unit for momentum is m times v, so it'll be kg times meters per second, so it'll be kg meter per second, okay? That's your quantity for momentum. So we can do that. Know the principle of conservation of linear momentum. Understand how to relate this to Newton's laws of motion and understand how to apply this to problems in one dimension. Okay, so the principle of conservation of linear momentum. This states that momentum is always conserved in any interaction where no external forces act. So your momentum before collision or before an activity, before collision, let's just write the heading. This is the principle of conservation of momentum, okay? What does it state? It states that momentum before collision is equal to the momentum after a collision. However, there's a condition after collision, provided no external forces apply. Sorry guys, no external forces apply, okay? Or you can say, instead of no external forces, you can also say provided collision takes place in a closed system. I'm sorry if the handwriting is a bit ununderstandable. I'm just trying to rush this topic very quickly. So that is what linear momentum states that, okay? Yeah. And how can we, let's just see what the specification wanted. Understand how to relate this to Newton's laws of motion and understand how to apply this. Okay. So to do this, if you want to, you can use this and relate it to Newton's second law of motion, okay? Newton's second law of motion is force is equals to ma. We do know that A is equals to V minus U on T, yeah, okay? So it can be written as F is equals to mv minus mu on T, okay? We skip the step, sorry guys. F is equals to mv minus u on T, which is mv minus mu on T. We do know that momentum is mass times velocity. So your mv and your mu is your momentum, initial momentum and your final momentum. So we can have the new equation F is equals to your change in momentum on time, okay? This equation can help you to, so you can have the change in momentum is equal to force times time. This is also known as impulse. That will be discussed later. But essentially, this is how you can relate the laws of conservation of momentum to this, okay? If there is no external forces applying, and if it's in a closed system, mv minus mu is equal to 0. So plugging into this equation, you'll have F is equal to 0 on T, and your F is equal to 0, showing that there's no resultant force acting on the object, okay? Or on the group of objects. We can just take this off. We have 7 topics left for mechanics. We'll do one more for this lesson, okay? Be able to use the equation for the moment of a force. Moment of a force is equals to Fx, where x is perpendicular to the distance between the line of action of the force and the axis of rotation. Okay, what is moment? Moment is defined as the turning effect about a pivot, okay? Let's say you have a triangle here that's not straight. That is also not straight. Let's just draw it like that. Say you have a beam on the triangle. This beam has this is a seesaw, okay? You have a person sitting here and a person of more mass, sorry. Okay, you have a person A sitting here, and you have a person B sitting here, okay? This is your pivot. Now, the person A will have his weight exerted downwards, and also B. But this will cause a different turning effect. This turning effect is known as moments. So, if this system is in equilibrium, if moment is in equilibrium, 2 conditions must be met. One is that there is no resultant moment and there is no resultant force. What do we mean by this? No resultant moment means the moment by A, which is the moment in this direction, should be equal to the moment of B in this direction, okay? The other condition is that there is no resultant forces in the system. So force A and force B, by our previous video of how to resolve a vector, should be equal to the resultant normal reaction force by the pivot itself. So we can just complete the drawing here and it'll result into a 0. So your free body diagram will just look like a dot if it's in equilibrium. So to calculate your moment, you will use your force times distance, okay? Let's just check the specification to see if we missed anything. Okay, no, we have not. So distance from here till here is your D1, and your distance from here till here is your D2. Let's say A has a mass of M1 and B has a mass of M2, okay? 1 second, guys. Number 15. Yes. To convert your mass, you'll need to multiply it by G and by G. So let's do weight 1 and weight 2. Your moment will be clockwise moment, which is the moment by B, because this is clockwise to the pivot. Sorry, which is by B, okay? Clockwise moment will be equals to force times distance, which is equals to W2 times D2, okay? If it's in equilibrium, you will simply equate this. So clockwise moment is equals to anti-clockwise moment. So W2 times D2 is equals to W1 times D1. And you can use that to find whatever the question is asking you to find. Essentially, that is what moments is about. In the next video, let's just tick that off. In the next videos, we will complete the remaining 6 topics, and then we'll move on to materials. So this is part 3 of the video. Yes.